All right, welcome back, everybody. We have one more talk, and then we are going to have a short break. The final keynote is at 4 o'clock, and at 5 o'clock, there's a social hour over at the Violet Crown, which is another building, and I think Patrick will give you details about that after the keynote. But let me introduce our speaker, is Kunal Mukherjee. He's recently a new applied scientist at the Zillow Group, formerly a postdoc over at Virginia Tech. And he's going to tell us about human-interpretable ML explanations in high-stakes ML, graph ML.
Hello, good afternoon, everyone. So for this presentation, I think I'm going to kind of glean over the technical details and try to give you the insights and the story behind it. So thank you for the introduction. So my name is Kunal Mukherjee, and I finished my PhD from University of Texas at Dallas. Then I moved to Blacksburg for my postdoc. And recently I moved to Zillow as an applied scientist. So in today's presentation, we will look at two different domains. One will be the real estate domain, recommendation domain. The second will be the security domain. So as my PhD, I did my PhD in cybersecurity. That's what my dissertation was. And at Zillow, since it's a real estate company, I worked on recommendation. So I will give a little bit of background so that we know like what terms mean and what we are doing, the little bit of motivation behind the projects, because I think when we talk about explanations, there is a big discrepancy between what a model developer wants versus what a CEO of a company or an actual consumer wants. So this work will mostly be on the fact that what a human or a native person who does not know model weights, biases, parameters would like to see. Okay, so starting off, I think the relevance of the two domains are very critical in the sense that there have been a lot of attacks currently. As you could know, like the recent wars has shown that the first infrastructure, what you attack is the power plant, grids. And these are mainly done by we call it advanced persistent threat. These are not something what you can detect by signatures. So traditional defenses have all been on the set that you have signatures and you create some kind of a hashes and you match it. But currently, the attackers have become smart. So they use what we call fileless malwares or malwares that live on the RAM. So there is no footprint. So how do you match them? So to match them, we have created what we call runtime defenses that basically look at the system environment, how the behavioral changes, what kind of applications they touch. And more importantly, these defenses have to work on all kind of environments, platforms. So when we talked about, like in the beginning, we talked about high-stakes graph ML. So where does the graph come from? So the graph comes from when we think about security, the security has to be on some kind of a platform, either tabular data or graph data, or let's say another kind of data. We will be working with graph data. So in the graph domain, think of a process that creates another process, which creates another chain of process, which writes to a file, and then the file connects to the internet. So this kind of captures the runtime behavior of a system very accurately. This graph is heterogeneous. You have different kinds of nodes, different types of nodes, different types of edges. They have different attributes. So how does this help us detect attack? So right now you might be questioning, this was our explanation. Why are we so learning about attacks? The thing where I'm going with this is the motivation. So currently, to detect attacks, one of the prevalent uses is using graph neural networks, because graphs can capture the dynamic temporal changes as well as different attacks, and those can easily be detected or kind of found out by graph neural networks, and they can be done in different granularity. So what we are mentioning that you can capture dynamic behavior, the long-range dependencies, and the fine-grained view. Now switching over, we have the real estate domain. For people who have been in Charlottesville, it will be a very difficult example, but where these slides were from Dallas. So in Dallas, post-COVID, there has been an exponential boom. So places where Dallas, you had houses, let's say 400K, post-COVID, those 400K houses are 600K houses. And then 600K houses are like $1 million houses, $1 million houses. Now, all the machine learning prediction models that have been out there are failing because it cannot capture the change of this user viability factor. So how can we kind of do better recommendation? Again, we can capture that using graphs. We can have a user. Think about Zillow. If you have used Zillow, you would know that as a user, you can be there, you can look at a listing, you can save a listing, you can view a listing. Listing means the property. Then the user is in a specific city where the house or the listing is located. And then the city where the listing are kind of captured. So this gives a very good tripartite view of the user's interaction or the user's graph. Now, based on the user's graph, if you predict or you recommend some property, you can get explanations effectively if you can capture the subgraph or like the exact interaction patterns. So next, I will kind of glean through this slide because this is most of the matrices. Just know that when we talk about explanation, we have to mention fidelity, that how good that explanation is to the model's actual prediction. And for recommendation, we use what we call the normalized discounted cumulative gain, NDCG, that basically says the recommendation that we have given you, this recommendation is how good and how relevant. These two things are captured. So for us, when we say that our prediction is very well, we say that this NDCG gain has increased by, let's say, 48% improvement based on what they traditionally used, which is histogram-based GBT trees. Now, when we were talking about security domain, we talked about process hubs. Similarly, for cities, explanations, we have what we call co-city hubs, such as Dallas and Fort Worth are two twin cities where people, when they're looking for houses in Dallas, might consider something in Fort Worth. For Charlottesville, I don't have a good example, but for Blacksburg, you can think of like Blacksburg, Roanoke area or Blacksburg, Christiansburg area. So these are what we call close-click cities where users share at least one common city interactions. And hub cities are basically cities which connect these two co-click cities together. So removing a hub city edge, that means that it will break the recommendation that we are giving. So this means essentially, if I recommend you a new house in Christiansburg, which is a little bit farther from Blacksburg, but under your price that you're looking for, under the bedroom, bathroom that you are in, then you might consider it. But suddenly, you are looking at Blacksburg, I recommend you Charlottesville, you will not. So that's why these co-club cities and hub cities are very important. And second, graph neural networks are actually structure-based learning. So when you break the structure, the learning falls. So this also helps with the fidelity metrics and also capturing the accuracy. So as I was talking over the explainability motivation, it was basically one, for security, you have to trust. And this is also similar for the recommendation. You have to trust the detection. You have to trust the recommendation. And second, there has to be justification. And this justification helps you get the guidance to make your model better. Because if you cannot give a justification for the model, it is black box. And I think post 2018, when GANs came into play and the first explainability, which was called LIME, came in, I think now secure or any kind of practitioners of machine learning are not willing to accept black box model. They want some kind of explanation. And I believe this also helps with the customer. Then for graph neural recommendation domain, it is important that we increase the customer's confidence, because a customer wants to know why we recommended something and why it is relevant. Because a customer, and now where I am currently working on, like giving a little bit of real life impact with this research, is now we want to tell the users when they're trying to look at houses some implicit signals. Maybe a person does not even know that roof only stays well for 12 years. So a house might have a new roof but can cost $5K more, which is better for them. So these implicit signals can also come from explainable things. So this is what I'm currently working on at Zillow, but nothing to do with this. I just thought of mentioning. So going over the, sorry, I think I went back. Yeah, so going over the security explainability part. So here what are the goals? Because in the first slide I mentioned that I won't be talking about model parameters or like any kind of model based or like what a developer would want. Here we want to explain the system, and this has to be done in a data-driven way. And it has to be done in a way that we capture the security domain knowledge, or many people call it the tribal knowledge. This has to be grounded on that. The explanation should not give you a random explanation which heuristically makes sense but had no connection to the model. So, as we were mentioning, the explanation verification is hindered because graph neural networks were inherently black box. And general purpose explainers that are out there are not security aware, so they were failing. And this is another critical learning that I found in research, is all kind of general purpose explanation that are out there, even for the recent use cases for agentic AI, they might not work for this kind of specialized domain. So for that domain, you have to create a harness so that you can create the explanation for that purpose. So for security purposes, because graph neural network uses the inherent structures, we decided to go with motif creation. Because this graph neural network is looking at some particular subgraphical structure in graph A and saying it is malicious. So my work was, how can we kind of inherently capture that and use that to basically train a surrogate model which is interpretable, like a decision tree. So the design was based on instance level. So for each individual graph, we should be able to say what is important, what is unimportant. It should be work in black box setting, so that in case in a security vendor, they do not tell you how the structure is, just for security reasons. So it should work on that. And second, it should be structure based. So the plan was, you have multiple anomalous graphs, you run your subgraph miner on those anomalous graphs, and you get the subgraph patterns. So these subgraph patterns capture the local behavior, and your graph structural matrices, like centrality measures, like triangle, captures the long-running dependencies. And I kind of merge these two. So here you can see in the subgraphical structure, the red blobs are the files, green are the processors, and yellow are the internet connections. And you see there are different kind of edges. Like for example, W is a write, E is execute, R is a read, and S this starts, like it invokes a process. Now, as you can imagine, these motifs can be very simple. It can be very diverse, like a very large, like let's say a motif of 30 nodes. So there has to be some control, such as the size. How many nodes are there? Diversity. Does it capture different processes, files, internet sockets? Support means how many times it has occurring. We don't want to capture very rare. We don't want to capture like all the common ones. And then coverage. Among all the data sets, how prevalent it is in different data sets. And then we do a different ablation study to come up with the hyperparameters for tuning. And then it was common to see that we prioritize support and coverage, because those were the primary differentiators. And then followed by diversity, finally size. And then we select the highest discriminant subgraph. Now, we understood the local changes, but these attacks are long running. The entire big graph, we have to understand the entire structure, how the different graph by themselves changes. So to do that, we characterize using the clustering measures and the centrality measures. So they can kind of give you a kind of a signature of the entire actual graph they're moving at. So for example, here, we're looking at the clustering coefficients, and we can see that the clustering coefficient of this the process here is extremely high, whereas the ones that will be on the edges will be very low. And similarly, like I am kind of brushing towards it, here you see a very central process, which is a kind of running very key, will have a very high triangular count, whereas let's say a process or a file on the edge, such as you just read or write to it, will be zero, will have nothing. So for a malware, where a malware, let's say, fork another malwares and talks to other, it will have a very high triangle count. And we will look at an example after this. So similarly for degree centrality, we have closeness centrality, betweenness centrality. Like if a node kind of connects two different hubs, it will have a very high betweenness centrality. And if it is like on the middle or the side, it will have a very low centrality. And similarly for different kinds of eigenvector centrality and cart centrality. So the entire pipeline was, we trained a surrogate decision tree with this discriminant subgraphs. Then we classify the subgraphs and we look at the decision path to figure out which important subgraphs were used for this classification prediction. And the pattern that are in the decision path are deemed as important. So here, let's say this pattern was thought to be important. For example, you have a file that is read by a process which reads to another process. So this is a very common type of malware where it kind of reads an information, forks another process, and it kind of writes to it. Then we see these two primary processes actually talking to sensitive files. You can think of these malwares where, let's say, it is reading your password.exe, or let's say your cookies/cookies. So you have this kind of three triangles. So now we take a actual graph where a Firefox process downloaded a malicious password manager and it read a lot of sensitive files. When we zoom into it, we see that the first pattern that we talked about, where the files are read by the two malicious processes and it kind of creates the second fork, are present. And this is the second structure we see where it reads a lot of sensitive files. And this kind of, after we have obviously looked into it and we saw that this explanation kind of captures the malicious behavior of this password.exe. And this showed that when you, even with a black box graph neural network, we were able to provide good explanation support. And if you just took the node, let's say the node's attributes, and you just look at it, it will also match with the ground truth of what it has happened. And for our evaluation, we had a kind of a long set evaluation where we went through different types of data sets that are out there. We even created some own test beds to make sure that we capture different kinds of attacks, different kinds of ecosystems. Then we kind of use different kinds of graph neural network structures so that to show that it is generalizable, and then also different kinds of state-of-the-art explainers to show that these explainers that are out there do not work that well. First, we had to show that obviously what our decision tree was, it actually matches the actual prediction. Then we show that the fidelity, that changing the important structure does indeed change the original graph neural network's prediction, is high. And fidelity minus means whatever we say as an important is actually unimportant. So you remove those, nothing should change. And we showed that we all perform the best in that, and you should be lowest. Then we looked at precision and recall. So in the precision and recall, we show that when we took the node attributes matched with the ground truth, how many of them matched. We saw that for Linux especially, it was kind of difficult, that almost all the explainers failed. And that is like one of the future works that we are currently working on for different ecosystem, how to get those to work. So like we had competitive performances. So three things become apparent with the GNS-based explanation, that the surrogate decision tree have high agreement, they have competitive performances and do perform well, better than the current state-of-the-art general purpose graph neural networks. And second, we are able to explain in terms of human-interpretable language. Okay, so the second paper that I will go over, which we call ZREX, like Zillow explanation. So the idea of this paper was that we want to explain the link prediction task to users. And here also we saw that general purpose explainers were not performing or not working that well. So here the idea was actually much more intuitive, in the sense for Zillow, everything is white box. We can look at the model output. We can modify the features. Here, so the idea was we will modify the features. We will look at the influential structures, and we will do structural perturbation to find out which are the important structures and the features. So when we have a recommendation and they have a very high kind of a cosine similarity between the users and the listing, that's how you know that which items or here houses should we recommend to the users. So the first thing we did was feature perturbation to find out which features are important, because a house has multiple features, has, for example, bedroom, bathrooms, lot sizes, roof structures, river view, or do you have a basement, do you have AC? And then certain things like when it was built, do you have, I think, lead? So there are a lot of different features, and these features have numerical, categorical, as well as Boolean, and location-based features. So we had to first find out which features are actually important for the prediction. Next was, once we found what features are important, we had to find out what structures are important. So that's why I kind of did the co-clicked city structures, so that when our users have clicked on different cities, what cities kind of are important for that recommendation. And we saw that co-click, to rephrase, like co-click cities are cities that the customers interacted with the listings and have at least one common edge. So we then identified which co-click cities are there between the listing recommendation that we did and they have clicked. Then we did a structural perturbation. Because it was a white box access we had, we could see that when we changed the embedding between the users and the listing, how it affected the recommendation. And finally, once this is done, we are able to capture the exact subgraph and the subset of features that helped. So for example, if we recommended a user new house with, let's say, more same bedroom, same bathroom, but 5K more, we are able to justify that by saying that you are getting new roof, your lot size is more, it is close to your kids' school, which in the long run will save you tax dollars. So we have that kind of added advantage. Similarly for that, one issue we ran into is like there is not a good real estate data out there, but lucky for us, we had the Zillow data, so we used the in-house data. We just tested on one graph neural network because that's what, in real estate, most things are run on like histograms and very simple kind of architectures. But luckily, because again, Zillow was using one of the, that time, like just simple GCN, we just trained on that. And we showed that for general purpose explainers, even a explainer by Amazon research, we were able to kind of show that we did perform better than that. And we had a very evaluation data set from Washington State. And one of the things currently we are working on is how to make the graph bigger per se, because graph neural network is good, but you have to store the graph somewhere. Graph in memory takes up a lot of space. And if you want to save a graph for, let's say, multiple days, multiple states, you won't be able to do it in your memory itself. So we need to split the graphs some way. Next, we saw that important features such as location-based features and lot sizes were important to users. And then places like fireplace, basement were not important. Fun fact, in Seattle or in Washington State, people usually don't have ACs, and many people don't have basements. So that's why it kind of matched with the ground truth of that state, but it will definitely change state by state. Then we saw that for us, our cosine similarity when we did the changes was one of the highest, and definitely removing the unimportant ones did not change it. So that again kind of matched with what we were thinking. Finally, for the co-click cities, we saw that when we removed hub cities, the prediction changed because obviously the cities that you had were important. And finally, like hub cities helped preserve the direction as well as the similar preferences. So the structure and the features were important. And finally, the three things we saw was that we were correctly able to identify important housings, hub cities, and we performed that time best GNN explainer for the recommendation system. And our main goal was to build confidence and provide increased user interaction. So as kind of future work, we wanted to work with robust and generalizable explanations because that's something we saw that both the domains lacking, that there were a lot of tribal knowledge being infused into the explanation, but they were not readily being worked. Then finally, how to bring in the temporal changes or the temporal nature in the explanation, because as time changes, your knowledge also changes. And finally, a new part of explanation is called counterfactual explanation. We wanted to work on bring that structure into the counterfactual explanation to make the explanation more robust. Finally, as a conclusion, I want to say that I have worked on like many different parts. A big part having in the provenance where I did what was my PhD topics such as differential privacy, federated detection, adversarial systems, and the current agentic forensics. And one of my very favorite area is explainability. So explanations, what I presented here was on the provenance-based explanation and recommendation systems. And thank you for your time. And I have open for questions. Yeah.
All right, we have time for some questions.
You mentioned doing a counterfactual. Will you do that with a Gaussian process or like a Bayesian structural type of like time series? Because like you said, the knowledge evolves over time, and if you're doing a counterfactual, you're trying to see that the treatment actually made a difference or it didn't make a difference. So
yeah, currently we are looking at the Bayesian one because for housing, priors are very easy to get. Like for example, you are a buyer or a renter, right? For I'm talking from the Zillow's perspective, right? So in Bayesian, like we are looking at first we have to first ensure that the priors what we are taking is actually the right priors. So we are looking at the Bayesian inference one right now, but yeah, like it's very initial stage of the research. So I don't have more answers for that. Yeah.
Awesome. Any other questions? I was a bit curious. The style of explanation you're giving still kind of requires a certain expertise, right? Like a non-security person will probably have difficulty interpreting these like graph structures. Have you looked into, making it so bozos like me can comprehend kind of what's going on?
Yeah, I think right now what we planned was that if we just give you let's say, the node attributes and tell you that, okay, this file was read by this process, and give a little bit of background on what this process does, so that anyone, even without security knowledge, can say, okay, a Firefox should not, let's say, be writing to a system file, or a Firefox accessing a system file is suspicious. At least if we can raise a suspicion in a let's say, security analyst's mind, I think that is a kind of an explanation, human interpretable explanation that we want to provide. Yeah.
Any other questions? All right. Well, thank you again.
Thank you so much.